Okay, let us see these two examples. Now we're asking when do we use the sine equation. The sine equation, you use it when you consider the initial condition to be from the middle or from the center of the equilibrium. In simple terms, from the center, from the center of oscillation or from the equilibrium position to anywhere, that's when we use the sine function, as we are going to see in these examples. But whenever you have the extreme ends, whenever you are from extreme ends, that's when we use the one for cosine. That's why it's whenever we are from up, that's when we are using the sine, the cosine. So let us see this example and you get the idea properly. So body makes harmonic motion at the rate of 10 cycles every after 2 seconds. So what does it imply? Anyway, between P and Q millimeters apart. If R is the midpoint of PQ, catch the time it takes the body to travel directly from P to R, then R to the midpoint of RQ. So, in simple terms, somewhere they are giving us this one, 10 cycles every after 2 seconds. It means that, so every after 10 cycles are made in 2 seconds. So it means that now this man is going to make, this body is going to make 10 cycles in 1 second. And if we have that, it means that now we have what we call frequency. Because frequency, we say number of cycles, this is now in 2 seconds. So from there we have now frequency, because we say frequency, a number of cycles made in 1 second. So from here, our F is going to be 5 hertz or per second. And now, so that if we have frequency, we can definitely get our period. So the period is always given by 1 over F, which will be 1 over 5. So our period is going to be, that is 0.2 seconds with ease. Okay, so after getting the period, let us see what we shall come up with. So if I have now the period, can I get my angular speed also? So that my t is given by 2 pi over omega. So if I have this is 0.2 equaling to 2 pi over omega. If I take this side, this one is going to be now, this divided by this, I'll be having 10 pi radians per second. As simple as that. So we have now all we need. So now we come up with a simple sketch. So if we have now, this is the idea I have. So this is the question I have. I have from P to Q. Okay, this is my Q. And then you know that R is the midpoint of PQ. So R is the midpoint of PQ, but these are 8 meters apart. So these are my 8 meters apart. Okay. Now from there, the question is, so if they are 8 meters apart, it means that this one is going to be 4 meters, and this is going to be 4 meters. Okay, they are asking now, find catching the time it takes the body to travel directly from P to R, from P to R. So there is that. A full cycle is when you come here, 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 here. That's when we have a full cycle. So this one is called a cycle. This is from here up to here is a half a cycle. So to get a full cycle, you come up to here, then you go back. That's when we have a full cycle. And the time it takes for us to make a full cycle from here, then you go back to this, is the period which we have as t. So meaning this is a quarter of the time we need to come from here to here is a quarter of the period. As simple as that. So it means that now, in first case there, our time is going to be a quarter of t from B to R. As simple as that. Because this is a quarter cycle. A full cycle is having 4 quarters. From here to here to here, then back to that. Hope the idea is there. So if you have this will be now a quarter, now times a period, which is 0.2. And this is going to give us, this is going to give us 0.2. I have 0.05 seconds. So the time is 0.05 seconds. This was for part A from B to R. As simple as that. The other way you can use is when you use the formula of calculating this. Oh, now it's that we are from here up to here. Now there is that we are from the extreme end. There you can use the one for cos, where we say our x is going to be equal to r, the amplitude, then cos of omega t, when you need this time. So from here, our x from this is going to be 4. Then, the amplitude there is going to be, then you can get our time distance from there. Anyway, from there, now, let us go to our part B. Okay, let us go to our part B now. Part B says, time taken for R to the midpoint of R cubed. From now R to the midpoint of R cubed, this is the midpoint. So, means that this is going to be 2 meters, this is going to be 2 meters. Now, this is the midpoint, our midpoint of R cubed. So meaning, it's now we are from the center, because our center position is R. If we are from the center, remember we are from the center always, now we use this function of sine. So from there we shall say, our x is going to be now R, then sine of omega t. Because the initial condition to remove the constant, the phase constant, we use the when it's here. It means that when it is 0, it means that even the distance covered is 0, the amplitude covered is going to be 0. That's why we use the those initial conditions. But if you are from here, you use cos, because cos works if the amplitude has been from here up to when you have the amplitude. But sine works if you are from the center. That's now from here now to here. That's why I'm using mine in that case. So from here, you see that my x, the distance I'm going to come from here up to here is going to be my 2 equal to the amplitude r. This is my amplitude, which is 4. Then sine of my omega by t. So I need that sine. So when I get this, I have 0.5 equal to sine 10 pi t. If you get the inverse, so our 10 pi t is going to be sine inverse of 0.5, which we all know that is going to be 30. Sine inverse of this, but 30, convert it now to radians. So we have now 10 pi t equal to 30, which is pi over 6. If you don't want this, then you press this when your calculator is in radians mode. Then you press this, and then after you divide, it's okay. So it's that now, this will cancel with that, so that my t is going to be 1 over 60 seconds, and that will be the time from here up to there. Okay, when I come to this now, I have a particle is moving in a straight line with a simple harmonic motion, and the period pi over 6 seconds. Given that the maximum speed of the particle is this, and it travels, find its speed 0.6 seconds after passing through the equilibrium position. So you do our simple sketch. This is what what I have now. So this is the measurement is my equilibrium point. Are they giving us the distance? No. So we don't have anything. Okay. So this is my equilibrium position. Oh. So they are giving my mean period. So the period is pi over 6, which I know is given, it's being given by 2 pi. Okay. There will be 2 first. Let me go stop. So if we have the period there, it means that now, to get our speed, we know that we always need, from the start now we are passing, we are doing that 0.6 seconds after passing through the position of equilibrium. So if we are passing here, it means that we are going to use the equation of our equation when we have side, because we are passing through the middle now to after 6 seconds. So the idea I'm going to use is when we have sine equaling 2r sine t. After putting in the conditions, that's when the first constant is phasing out when you're passing through the middle. And you see that now we need this, we have the time, we need this. The amplitude, see? So let us see what we need. The amplitude, we need this distance, we need the amplitude, we need the omega. We have the time, then let us see how we get this. And we know that our t is given by 2 pi over w. So it's that this one now, this one is pi over 6 equaling to 2 pi over w. See, this one is going to cancel, and you see my w is going to be, when I multiply there, I'm going to be adding 12 rad per second. After getting that, now they are giving me at the maximum speed. So they are giving me maximum speed. So, and that Vmax, you know, the formula, whenever they talk about Vmax, this is what we use. You get the amplitude, then times the angular speed. If they talk about just the velocity, you use the other formula of V squared equaling to omega squared into r squared minus x squared. So they are giving us this as 36. In the amplitude, we have this as 12. So when I simplify that by it's going to be, because this is the maximum speed. So I have this now. So this one is going to be 3 meters. So meaning, I don't know what this is from here up here. Now I have this as 3 meters. Also implies from here up there, I'll be adding 3 meters. So it is. So now, what don't we have? We have the distance we are going to cover is 3, the amplitude, but this is now the displacement. If we need the speed, it means I can differentiate this. When I differentiate this, I'll be having now speed. Remember, our velocity is equal to x line. As simple as that. So, if we differentiate this, I'll be having x prime equaling to r. When we differentiate this, we differentiate the r, we get that. Then we differentiate sine, we get cos of omega t. So that's how I can easily get this, because I'm passing through that set done. So now, this is x prime is going to be my velocity. This is in simple terms the same as dx dt. So to differentiate this side, we differentiate the arrow, what we get multiplied to there, and then that's what we'll be having. So my v now is going to be, I have the amplitude as 3, the omega is what? The omega is 12, then cos of the omega is 12, then times 0.6. And so from there, you get to ask. Your calculator should be in radians. So there I'm going to get 12 times 0.6. Cos answer times 36. So my velocity is 21.99 meters per second. So this is my velocity as simple as that. When you have that, let me show you something else. Okay, if you have a question why I didn't use this omega squared into r squared minus x squared, you have that because after this x is always the distance from the displacement. So after that, number 0.6, after that switch is 0.6 seconds, I don't have this displacement from the equilibrium to where it is after 0.6 seconds. That's why I couldn't use this formula here, because I don't have this displacement from the equilibrium position after 0.6 seconds. So that's why this one wouldn't work, and that's why we had to use this. And why I use this side, I think I've told you the reasons already. So that's it, and I wish you well. Also here, when the x equal into sine, I think you would have seen that we had the amplitude, but displacement we never had. This is always the amplitude, so never had a displacement. That's why I couldn't use that. So here now you have from here you have now the displacement from the point, which is 2. But here we never had it. We never had that displacement there. Anyway, that's it. I wish you well. So I think we see that our x is missing and we are not happy.